Hello everybody, we're going to look at some periodic behavior here. We're going to continue modeling our sine waves and cosine waves in some real life applications here and some complex diagrams in certain cases. So 2 examples for you today. The average daytime temperature for a city is given by a given function where T is the time in months after January. Sketch the graph for D against T for 0 to 24. Okay, well, what can we find out straight away? Well, we can see clearly with the 5 being there that the amplitude, that's the size of the wave, is 5. We can also see that the principal axis, that is the axis which we rotate around, is going to be at y equals 20 because we have a 20 there. It's a cosine wave, so we're going to start at the top. So if you think about it, well, our maximum value, if our principal axis is 25 and our amplitude is 5, our max value that we're going to start with is going to be 25, and our minimum value is going to go down as low as 15. Final thing to worry about is the period of the graph, how long it takes to repeat itself. So we take 2 pi, the original, and we are going to divide that by pi over 6. Well, that is going to be the same thing as 2 pi multiplied by 6 over pi. The pi's will cancel, and we are going to have a period of 12. So that means in our range of t being between 0 to 24, our graph is going to repeat itself twice. So let's have an attempt now at trying to draw this. So we have some axes here, look, and we're going to go from 0 to 24. We have 12 there in the middle. That's how long it's going to take to repeat itself. And we are going to be rotating around 20. We've shifted up 20. Okay, so our max height will be 25. Our min height is going to be 15. I know my scale is a little bit off. Okay, we're doing a sketch for these. Okay, we don't have any graph paper or squared paper. All right, we're just doing a sketch. So we are going to start at the top because we're a cosine graph. We're going to get back to that top when we get to 12. In the middle of that, look, at 6 will be at our low point. We're going to be hitting that principal axis at 3 and again at 9. So this will help guide us. Let's carry that on again and do it again. Look, at 18 hours past, we will be again at our minimum. And that means at 15, we'll be hitting the principal axis. At 21, we'll be hitting the principal axis. At 24, we're back at the top again. So we can use this to help guide us. Okay, so we're going to go something like this through that principal axis, back to the top at 12, back down, minimum at 18, and then back up to the top by the time we get to 24. Okay, so this is our t-axis. All right, we have temperature going up, don't we? Degrees C, temp, and there is our graph. So, part B, find the average daytime temperature during May. Well, average daytime temperature in May, well, that is going to be when T equals 4 because it's the time after January. So if January is at the beginning, February is at 1, okay, and so on and so on. May is going to be when we are at 4. So all we have to do here is sub 4 into our function, right? So we're going to do 5 times cosine of 4 times pi over 6, so 4 pi over 6 plus 20, and this is going to give us our answer. Now, I'm going to skip through the unit circle things, but cosine of 4 pi over 6 is the same as cosine of 2 pi over 3, and that is going to be negative a half. Plus the 20, we're going to end up at 17.5 degrees C. Okay, so there is our average temperature for May. Okay, so what we did there, by the way, let's just make a good note of this. We'll say we put in 4 into this, right? D of 4, if D is our original function. C, find the minimum average daytime temperature and the month in which this occurs. So the minimum, well, that will be at these minimum points here, look, and here. Okay, that's when the minimum average daytime temperature is happening, and that is happening at 6. and that is happening at 18, okay? And of course, if we've got 12 months in the year, it's the same month both times, and that is going to be in July, all right, when T is 6, counting on from January, all right? Okay, let's look at another example. So question 2, we don't even have a function here. We're going to have to figure out the function ourselves. On a hot summer day in Madrid, Antonio pays careful attention to the temperature. The maximum of 41.8 degrees Celsius occurs at 3:30. The minimum was 27.5 degrees Celsius. Suggest a sine function to model the temperature for that day. Okay, so we've got some clues here to help us. We know we are looking for a sine function. First of all, I think we should try and find that principal axis that we're rotating around. So that's going to be like the average of the maximum and the minimum. So if we take the maximum, which is 41.8, and we add to it the minimum, and we divide by 2, we're going to have that oscillating number that we're going to rotate around. So that is going to be 34.65 degrees C. All right, so that is going to be where we have our principal axes. Okay, next thing, the amplitude of this thing. Well, if we take that maximum minimum and find the difference between them by doing 41.8 minus 27.5, that's going to give us the difference between the max and the min. So if we divide that by 2, we're going to have the amplitude of the wave. So that's 7.15 degrees Celsius. So that is going to be our amplitude. Next thing, well, we can think about the period of the graph. And of course, if we're looking at this daily, all right, we're looking at a sine function to model the temperature for that day, then we're kind of told that the period of the graph is 24, right? So period is 24. So that means that that number in sort of next to the x in the sine function we're looking for, we usually call it b. Well, that will be 2 pi divided by 24, or in other words, pi over 12. So we've got that number that goes in there. Okay, carrying on. Well, what else do we know? We've got some sort of phase shift to the right or to the left happening because we do not have that principal axis 0 starting at 0, right, in the middle of the night. That is not the case. We've got to work out something when we've got this maximum at 3:30, right? So that's going to be a bit tricky to think about. Well, this is 9.5 hours after midnight, right? Sorry, before midnight, I should say. So that means we have had a shift, haven't we, of 9.5 hours to the right. So we can think about that when we put together our sine function too. We've gone to the right by 9.5 hours. Now, putting all this together, I don't know what we're going to call this. Let's call it T, right? Capital T for temperature. In terms of time, lowercase t, well, let's put it together then. So we've got the amplitude, 7.15. So it's 7.15 sine of. We know that we've reduced the period and we know what goes in front. It's pi over 12. But we've got this phase shift to the right of 9.5. So if we do x minus 9.5, we're going to have a correct phase shift. And finally, we just need to add on the 34.65. We worked out where our principal axis was because we've shifted this whole thing up to oscillate around that particular point. Okay, so there is our sine function, putting these pieces together. Okay, so with that having been seen, you should be able to have a go at the exercise in front of you now. Good luck.